Like an idiot, 30 minutes before I decided to delete everything I had in terms of slide content. Of course, just because I wanted a challenge. So if anything feels a little off or some of the spelling's not quite right, it's because I'm playing on hard mode. So, we're going to talk about software-defined radio. A lot of you guys, I know some of you have the Flex system, the software-defined ham radio. I'm not going to be going into that sort of topic tonight. It's going to be more on the raw, actual software-defined nature of software-defined radio, as opposed to commercial offering. All right. So the first thing, I'm sure you're all aware, software-defined radio relies on the digital signal processor. Digital signal processor is a pretty expensive, fancy chip that's able to take large amounts of audio signal or radio signal, if that's their particular use, and convert it into digital information. So we can digitize it, turn it into binary, as a simple way of thinking about it. So the particular way we do this is with a piece of hardware that includes one of these. The one I've got with me tonight, I'll circulate it around, but I will need it back. It's called the RTL2832U. The cool thing is it has a terrible name. The other cool thing is it's only $30. It does 64 megahertz to 1.7 gigahertz. And again, this is $30 Canadian shipped. So it's a fantastic little unit if you want to start playing. Pretty much everybody who starts in software-defined radio, unless you've got thousands of dollars in a research laboratory behind you, you're going to start out with one of these. It's pretty cheap hardware. It uses a Realtek chipset, same manufacturer that makes some Wi-Fi chipsets you may have heard of. So the only downside to this, besides the fact that it is kind of limited in terms of a software-defined radio, frequency-wise, is it's receive only. So you cannot broadcast using this particular set. There are others you can purchase, but they're going to run you a little bit more than $30. $30, by the way, is the cheapest chipset you can get in at. So if you are looking to play with this, recommend you take a look. So there are alternatives, as I said. One of the popular ones most recently, it's called the Hack RF1. Not too much detail on that. I don't have one with me. I can't really show it off. If you're looking to get into that, you've got 1 megahertz to 6 gigahertz. Pretty much as some of you guys would call it, DC to daylight. You can get the ham bands if you use an up converter on it. The other cool thing is this does both receive and transmit. If for anybody who's wondering, the transmit is only a few milliwatts, but as you all know, you attach a linear to the outside of that and you can pretty much put as much power as you want into the signal until it gets out of hand. But for a system like that, you are looking around 350. Still extremely reasonable from where software-defined radios were 5 or 10 years ago. Before this, a software-defined radio would cost you around $1,000 to $1,300, so they've recently come down quite a lot in price. Thanks to cell phone technology, mostly. So, that's the hardware. Where's the software? Assuming you're all asking. So the cool thing is once we've digitized all of that radio wave into data, we can then use software to manipulate it. For our particular purpose tonight, we're going to be using a program called New Radio, or GNU Radio, some people prefer to call it. New Radio is a prototyping tool. It allows you to very quickly and easily set up flow paths for this data. The problem is directly off the chip you're getting ones and zeros. It's just representing, if you think of a waveform, each of the different points along the wave have an individual readout of the value, and it's sending that to you at megabytes per second or even gigabytes per second, depending on which model you choose. We need some way to actually process it, to not only be able to hear it, but also to see it, and sometimes even decode it for digital protocols. New Radio makes this pretty simple for us. The reason is it relies on a technology called blocks. We probably learned about them when we were all young. But blocks are fantastic because it means we can encapsulate functionality inside of components where we don't actually have to know what's going on, so much as we know what we can do with it. As an example, if you think back to math, the operation addition is very similar to the way a block works. You can take one number on the left and one number on the right, and you put them through the addition block and you get some output, right? The actual way that works, you don't have to 100% know, so long as you understand that you can use it to your advantage. This will become much more clear when we get into the demo. For anybody who's got a bit of a programming background, you can go a little bit further than the blocks model. The blocks model is a way that allows you to quickly manipulate Python or C++ code. I'm not going to go into the details, and the best part is you don't actually have to use the tool. But for anybody who's looking a little bit more adventurous or needs some extra oomph out of the software that they can't quite get, this would be the way you'd go about it. So, New Radio Companion. This is actually the tool you're going to use out of the New Radio suite. New Radio is a bunch of utilities all working together in that sort of block model. The Companion is a quick and easy drag and drop utility to move around the parts you need to accomplish a task. So, I have DVDs with me. I only managed to burn 3 of them. They contain an operating system as well as all of the new radio utilities. If anybody's looking for a copy at the end of the night, again, I have 3 of them with me, so I may not be able to get you one this evening, but if you are looking for a copy, I can happily pass that along. It's a Linux Live CD running Ubuntu, and again, it has everything you'd need to be able to work with any of the stuff we're doing tonight. Except for the hardware dongle, you'd have to pay $30 to get one of those. I didn't bring samples. I have 5 demos lined up, each of them sort of in an increasing difficulty of what you can do with the software. We're going to begin by building a dial tone in the software, using a function generator and mixing a couple of signals together. We're then going to move on to a busy signal, which will toss in just a little bit more confusion, or understanding to see how these blocks fit together and how we can actually build upon them. We're then going to move on to visualizations. This is where we're going to see the general FFT, the fast Fourier transform, that's the wave you get, as well as a waterfall. After that, we're going to move on to a sort of very simple how you would use this to go about networking with radio. So for anybody who's looking to play with protocols like Wi-Fi, Bluetooth, Zigbee, or even DMR, this would be the sort of area where you might want to start to jump into, because it allows you to run TCP/IP, with the internet protocols, over your radio. So it's kind of a fun way, as well as take data out of those protocols from other uses. And finally, I'm going to move on to attempting to build an FM radio. One of the things you'll notice is there's a lot of acronyms. It gets very heavy in terms of technical jargon. Don't worry if some of it's going a little over your head. It goes over my head too. Feel free to ask questions along the way. I'll be happy to answer what I can, and whatever I can't, I will try to come back to you with a good Google and Wikipedia response. So, before we move on, does anyone have any questions? No? Alright. Am I talking too fast? I know it's one of my downfalls. Faster, slower? Just right? Perfect. Alright. So, when you launch New Radio, you're going to end up with a screen that looks like this. So, what we have here is a little confusing at first, but pretty simple once we actually get down to it. Along the top, you have your traditional toolbar and icon buttons that'll get you different things that you need pretty quick. This main area in here, where we have these 3 little blocks already lined up, this is the canvas, as you might call it. This is where you're going to put the blocks and link them together to perform functionality. Along here, I have the 5 demos that I'm going to be doing tonight. We're already currently loaded up on the first one. If I scroll down to the bottom, you can see I've already created it just in case I can't quite get it to work. The demo gods aren't quite with me, but I will try to do as much of it live as possible. At the very bottom, we have a debugging window. This will actually show us any sort of code or errors that we have. They are quite cryptic, unfortunately. They're not very user-friendly, but you can usually make out what's going wrong if you read them quite carefully. And then along this right-hand side here are all of the blocks, or rather, all of the folders that contain all of the blocks. It's quite exhaustive, and the first time you try to look for anything, you're not going to be able to find anything you want. I pretty much exclusively use this button right here, or the Control-F shortcut. This allows me to search for a block by name. Alright, so what we're going to do in this first demo is we're going to produce a typical dial tone. Alright, I've created a little note here for myself. For anybody who's not familiar, a dial tone is created by 2 frequencies using a sine wave. You have a 44 Hz signal and a 440 Hz signal and a 330 Hz signal mixed together to produce that typical wah sound you get when you pick up the phone. So, what we're going to have to do is we're going to have to pick up a generator. So, signal source. Again, quite quickly I had to toss this together. We're going to need 2 of these, one for each of our different source. And we'll just drag them out here. So as I said, this is where you start to see the block functionality. I don't need to know how to produce a sine wave. I don't need to know the type of data format interchange that these blocks use. It gives me particular options I can configure on the block, outputs, and inputs. Alright, so let's configure our first source. If we double click on it, it'll pull up a configuration wizard here. All we need to modify for this is going to be the first frequency. We'll set this one to 330 Hz. In here, all measures you put in are always in base units, unless stated otherwise. So for example, if we want to use megahertz, we're going to need to type a lot of zeros, or we can use exponent notation like E6 to get megahertz. But for this, we only need hertz. So we'll hit OK on there. The other thing I should also do, for right now, we're also going to need to set the amplitude to half. That's because we're going to be adding the two signals together, and if we don't do this, we'll end up with an amplitude of 2, which will completely peak and start to cap, and it won't sound quite right. So we'll do that. And here we'll do the other tone. We'll set the amplitude, 0.5. We then come over here, we pull out an add block, connect this to this, this to this. We now need an audio sync. So a bit of notation for you. New Radio considers outputs sinks and inputs sources. So when we see something like audio source, this allows us to pull in audio, and audio sync allows us to send it out. Pull that in here. So just change the type here. You can change the type quickly by pressing the up, but the other way to do it is output type in here. Unfortunately, again, to go through all of the gory details of what's going to be happening takes quite a bit of learning and understanding. For the most part though, once you get your feet wet, the process becomes much easier. So I'm going to connect here to here. I then should be able to save it and run it. And if everything worked well, there's your traditional sine wave. Or double sine wave, I guess. So what we're going to do now is we're going to convert this from a dial tone on the fly, because I'm not even going to move off to example 2. I'm going to move this into a busy signal. Yeah, busy signal. That's that wah, wah, wah you typically hear. So for that, I'm going to need this note right here. If you remember, pretty simple. Most phone tone frequencies are set up of 2 signals. In this case, we're going to need 480 hertz and 620 hertz. So we have 620. We're also going to need something else. Because we want it to pulse on and off, we're going to need to do something pretty fun here. We need to change the frequency to 1 because it comes on and off with a signal frequency of 1 hertz, or 1 per second on, 1 per second off. And we're going to change it from a cosine wave into a square wave. Now what we can do with this, I just move all this down here. We pull this up over here, pull up a multiply function right here, change its type, change this as type, connect this to one of the sides of the multiply. So what this is going to do is it's going to produce an amplitude signal between 1 and 0, oscillating with a period of 1 second. Which means we can multiply the output here by that, so that we get it on for 1 second, off for 1 second. We then connect this to our output, we run it, we get. Everybody's familiar with that sound, I hope? Alright. At this point I'm going to stop for any questions anybody has. This has been quite confusing and I've been moving quite quick. Anyone?
Are you going to have some more sounds? We can hardly hear the sound back here.
I would...
You got an Ethernet jack on that?
Oh, an Ethernet jack?
An Ethernet jack?
Not really, no, unfortunately.
No earphone jack?
I do, but it's broken.
Oh, okay.
So, sorry about that.
You can back here, it'll work.
I'm more than happy to bring it back there if you want, so you can listen to the sounds.
Okay.
Okay. Alright, so any other questions before I move on? Alright.
Is this open source?
It is, yes. Open source, entirely free. The long and the short story was back when the FCC decided that television should have a do not copy bit, a bunch of people got really angry, put some money behind their words, and created this so that you could either choose to use or not use that do not copy bit. And now we have a fantastic software utility developed by many different companies who have interest in using it. So, but it is entirely free and open source. So it'll run on Mac, Windows, Linux, everything. Isn't it great what happens when people have money and they're angry? Anyway, example 3. So here what we're going to be doing is we're going to be looking at visualization. So just for the interest of time's sake, I'm going to drag this up and explain what goes on here. Alright, so just going to enable these blocks. What we're going to be doing is we're going to be using, and I did not connect, where did the dongle go? Perfect, there it is. In order to visualize something, we need something to visualize. Alright, So all I've done is when you purchase this, it comes with a stubby little antenna about this big. I cut the end of the coax, put on a UHF connector, so that I can now connect this to my handy dandy mobile antenna, and hopefully we can get some good reception down here. So, got this in here. Alrighty, that should be good. So what I'm going to do here, and I'll just kind of use the cursor to explain as I go along. And I can't do it sideways, so I'll have to do it from behind. Alright, what we've got here is we've got a source block. This allows us to talk to our little dongle and request information out of it, specifically the audio stream. We're going to tune to a particular frequency, and for those astute listeners playing along, you might notice I've set it to 147.12 megahertz for no particular reason whatsoever. What we've also got is we've got a particular gain setup. It's 20 decibels. Doesn't really matter too much, but we're going to do that just so we can hopefully get something fun on the output here. If we move over here, we've got two different visualizations going on. We have, there we go. We've got a waterfall sync and we have a frequency sync. So what's going to happen, hopefully, if everything's quite right, we should get a waterfall on the top and a frequency down below. Both of them, or actually all three of them, have been tuned to this particular range up here. So if we go over here to pull it up, for the source we would type in RTL, and we would pull up this RTL source. This Osmocom source allows you to pull from multiple different dongles and makes the process a little simpler, but both work the exact same. And then for visualizations, it'll be under instrumentation. There's two different graphics toolkits. Again, the details get a little hairy, but pretty sure you can follow along with a good tutorial. So in here you've got different types of outputs you have. You've got, what do we got? Burr curve sync, we got the constellation sync, we've got the frequency sync, which we're going to be using. Histograms, numbers, you've just got a general GUI sync. I'm not exactly sure what that does, I haven't played around with it yet. But you've got time raster, time sync, you can bring it in as a vector, or you can bring it in as a waterfall. For our purposes, I'll just bring it in the two because they're typically the most visually interesting. But feel free to play along with, or play around with whatever you'd like. So, for this particular demo, we're going to give it a run. We get a fantasy output here. So this is a pretty poor color scheme by default, unfortunately. They give you 4 different color schemes and they're all terrible. So this was the best one I thought would show up. It's quite a little undersized for this display, but you can see clearly. Up at the top, we have right here our waterfall output, and below we have our frequency visualization. By scrolling around inside the box, and not the page, you can increase or decrease the scale of the output for both of them. So we'll leave that alone just a little bit. I've also added to the top here a scanning slider that would allow us to change frequencies, but I'm not going to be playing with that for this demo. So if I take my handheld and I turn it on, and I set it to the lowest possible power setting because I don't want to blow anything up, and I transmit. This is VE3ZSH testing. Perfect. It is delayed. Unfortunately, when you're processing this much data, it is quite slow, but you can actually see there on the waterfall down at 135 megahertz, which clearly shows that this has been tuned correctly. Cheaper donglers will have to be tuned more readily, but you can see that right there we have our transmission that was recorded directly through the RTL dongle. You won't hear anything because we don't have an audio processing going on. To do that, we'll have to do FM demodulation, which we'll be doing in the next tutorial. But for our purposes, it's pretty straightforward. Again, this is VE3ZSH testing, just showing off the new radio package, picking up my voice and showing it on a waterfall. Fantastic. Alright, questions, comments, concerns, queries, quandaries? No. Excellent. Glad to see everybody's enjoying it. Let me just close that to get out of it. Alright. I think I'll do example 5 before I do example 4 just for our purposes. So, I'm not going to try to reproduce all of this. It takes quite a while to do. But, let's just enable all of it here. What we're going to be doing is a series of steps to the input to slowly convert this from unusable input to audio. So what's going on here? Alright, so we take our input, and I've set it to 107.1 megahertz. If anybody's got a nice long drive and they typically listen to the radio, you may or may not know this frequency. We're going to take that over to a rational resampler. All this is going to do is when we're recording, we have to pick a particular number of samples per second that we want to take. For our purposes, we set up initially that we want to take 2 million samples per second. But we're going to convert that down to about 1/4 of that, or 500,000 samples per second. We're going to pass it through a low-pass filter, just to get rid of all of that high staticky noise that you're not going to really want to listen to. Then we're going to pass it to a wideband FM receiver. All I need to specify for this is going to be the quadrature rate and the audio decimation. The cool thing about this is, again, I don't need to know how to perform FM demodulation. It's all taken care of thanks to the block. This is going to convert it between data types, and we're going to take it through another rational resampler. When we're doing the FM demodulation, we want a nice, crisp, clear signal, but when we're putting it out to audio, we only need, in this case, 48 kilohertz. Anything more, I mean, you may be able to, if you're an audiophile, claim that you can hear more, but for our purposes, and especially for those in the back, it's not going to make much difference. So, if the moon is aligned correctly and everything is quite right, and we can get 107.1 megahertz down here, we should be able to... Static. Okay, this was working at one point. You should hear crystal clear as day, some rock and roll right now, but unfortunately we're not picking up much downstairs. As well as you can see, I'm using a 440 and 147 tuned antenna, so it's not going to work quite well for picking that up. But nonetheless, this should technically work. Alright, the last one for all of you geekier people out there who prefer the Linuxes and hacking into the Wi-Fi and stuff like that. We've got a setup here that allows you to do some pretty cool stuff. So one of the things new radio is really powerful in is it lets you analyze digital signals, specifically digital signals that use protocols like DMR